Hello and welcome to this video on section 7.3, the rules of replacement. In this video I'm going to go over the first 5 rules of replacement. These are going to work a little bit different than the rules that we saw in sections 7.2, 7.1 and 7.2, because these are actually rules that you could substitute into parts of a proposition, into parts of a premise. Remember that in 7.1 and 7.2 we were using premises to deduce further premises to get a conclusion. Well, what's going to make these rules here in 7.3 different is that we can take parts of those premises and substitute them for the for the versions of the rules that we'll see here, or for the application of the rules that we're going to see here. These are also, you can also think of them as equivalences. And so here's the first one, the Morgan's rule. And that basically means that in this case, the not P and Q is equivalent. And in fact, these little 4 dots here means is equivalent to not P or not Q, and vice versa. Not P or not Q is equivalent to not P and Q. And so with the Morgans, we also have this other variation where not P or Q is equivalent to not P and not Q. So you can think of them as equivalences, and we do have truth tables that show that they are in fact equivalences. So here we have commutativity, which is the one we're going to do next. So this here is not De Morgan's. This is commutativity. Commutativity basically means that P or Q is equivalent to Q or P. So in this site, the triple bar means equivalent to. We don't have the 4 dots here. We have the triple bar, but they mean the same thing. It means that these are equivalent to each other. So P or Q is equivalent to Q or P. So as we can see, this truth table shows us that under the main operator here, we do have them all as true, which basically means that they're both equivalent to each other. That no matter how we shift or change the truth values under the P or the Q, under the main equivalent sign here, it's always going to be true. So we can build truth tables for all of the ones we're going to see in this section, and then also the ones that we're going to do in the next section in 7.4. So let's go back to De Morgan's. So again, remember that it is an equivalence rule. What I'm going to do in this video is pretty much show you why there's meaning logically here. So this is not all just mathematics. It is very mathematical in a way, but these are logical equivalents. So what I'm going to mostly do here, for the most part, is show you why these are in fact logical equivalences. So let's take an example here. Let's substitute let's substitute P for a proposition and Q for a proposition. So if we take the first application here of De Morgan's, remember we said that not P and Q is equivalent to not P or not Q. The question is, how do we read this in ordinary language and regular language? Okay, well let's do that. Let's let G represent a proposition, which, remember, that's what that is. That's what that does. It does represent propositions. So suppose that G represents the proposition the grocery store sells textbooks, and suppose that T represents the proposition the toy store sells textbooks. So basically what we have in the top here, in the symbolized version of this, is something that can be read a couple of different ways. I could read it as not both the grocery store sells textbooks and the toy store sells textbooks, right? I could say that not both of them sell textbooks. I could also read it as it is not the case, and remember that's just a negation, it is not the case that the grocery store sells textbooks and the toy store sells textbooks. I can read it that way. Both of those basically express what that is saying logically. Well, then it's easy to see how if we say something like not both the grocery store sells textbooks and the toy store sells textbooks, then that is logically equivalent to neither the grocery store sells textbooks nor the toy store sells textbooks, right? Those are two logically equivalent things. We're basically saying the same exact thing logically, um, if we say it in those two different ways, right? So that's what I want to show you for the most part in this video, why these are in fact logical equivalences. Okay, if we take the other variation of De Morgan's here, which is this second one here, where we have the tilde outside of the parentheses, and then we have the wedge, the or. Well, then again, we substituted for the same propositions. G still represents the grocery store sells textbooks, and T still represents the toy store sells textbooks. Well, then what this is saying here, in this one here, is something like, it is not the case that the grocery store sells textbooks or the toy store sells textbooks, right? Something like that. It is not the case. Well, we can very easily see that that basically means the toy store, I'm sorry, the grocery store does not sell textbooks and the toy store does not sell textbooks, right? So basically, this one here, I'm pointing with my mouse, is equivalent to this one here, right? Saying it is not the case that the grocery store sells textbooks or the toy store sells textbooks is the same thing as the grocery store does not sell textbooks and the toy store does not sell textbooks. So we can see that De Morgan's is very logically intuitive. We can see why these things are logically equivalent. Okay, let's go to the next rule, which is commutativity. And by the way, these do have abbreviations. We have COM here for commutativity, and for De Morgan's we have DM. And the abbreviations are there because we are going to use them as rules, just like we did with section 7.1 and section 7.2. And we do need to cite the rules as we deduce or apply them in proofs. So keep in mind that that's why those are there. That's going to be our shorthand way of citing the rules. Okay, so with commutativity, basically what commutativity says is that the order, when we have a wedge and a dot, basically when we have a disjunction or a conjunction, the order doesn't matter at all, right? That we could switch P or Q, and that's equivalent to Q or P. And then the same thing with P and Q. P and Q is logically equivalent to Q and P. And so this is easy to see. If we have Francisco studies logic, let's let that be F, and John studies logic, let's let J represent that. Well, then basically saying Francisco or John study logic is logically equivalent to saying John or Francisco study logic, right? Nothing is lost logically there. They are in fact equivalent. So that's easy to see. And then with conjunction, the same thing happens. If we say Anna goes to the movies, let's let that be represented by A, and Linda goes to the movies, let's let that be represented by L. Well, basically, Anna and Linda go to the movies is logically equivalent to Linda and Anna go to the movies, right? Those basically logically mean the same thing. And so commutativity is very easy to see in that way. In mathematics, if you want to understand this in arithmetic, there's commutativity. There's the commutativity of addition, right? 3 plus 5 is the same thing as saying 5 plus 3, right? And then it also works with multiplication. 8 times 2 is the same thing or equivalent to 2 times 8, right? So we see that in mathematics we have the same kind of idea. And in that case, it only works for addition and multiplication, while here it only works for disjunction and conjunction. Okay, our next rule is associativity, and that's abbreviated as ASSOC, and is pretty much similar, very similar to commutativity in the sense that in this case the parentheses don't matter. That we could switch to parentheses, and in a way we're not really switching anything logically. So it also applies to disjunction and conjunction. So notice that that's another similarity with commutativity. And so what this is basically saying is that P or Q or R is equivalent to P or Q or R. So it doesn't matter if we shift those parentheses. And then the same thing applies with conjunction. P and Q and R is logically equivalent to P and Q and R, right? It doesn't matter where we have those parentheses. If we shift them, these are going to logically mean the same thing. So let's stick to the Anna goes to the movies example, and let's add Tom here. So Anna goes to the movies is A, Linda goes to the movies is L, and Tom goes to the movies is T. Okay, well, if we basically say Anna or Linda or Tom go to the movies, that is logically equivalent to Anna or Linda or Tom go to the movies, right? So notice that what I've done here is that I just shifted the parentheses from over here to over here, and I'm just modeling this based on the rule, and that just means the same exact thing, right? Logically, we don't lose anything if we shift the parentheses there. And then, of course, the same thing is true with conjunction. If we say Anna and Linda and Tom go to the movies, that's what we have here. That would be logically equivalent to Anna and Linda and Tom go to the movies. That's what we would have here. Again, logically, nothing is lost. We're basically saying the same exact thing, right? So associativity is also intuitive. It's very easy to see. Let us go to distribution. Now this one is not easy to see in terms of natural language. So I'm just going to explain, or actually just basically read how this one is described in our textbook. Basically, with distribution, I'm quoting here word for word what the textbook says. When a proposition is conjoined to a disjunctive statement in parentheses, and that's what we have here. A proposition is being conjoined. There's the conjunction, there's a dot, to a disjunctive statement in the parentheses. That's this part over here. That's the Q or R. Well, that basically means that is equivalent to basically the disjunction of those two conjunctions, right? This is P and Q is a conjunction, P and R is a conjunction, and then we have them disjoint. We have both of those being disjoint, right? So let me read this again word for word. When a proposition is conjoined to a disjunctive statement in parentheses, or disjoint to a conjunctive statement in parentheses, the disjoint part is this one over here, the rule allows us to put that proposition together with each of the components inside the parentheses, and also to go in reverse. Okay, so again, this one is not immediately obvious. It'll be hard for me to use an example from natural language. So again, you just have to trust the truth tables here. And in fact, if we go back to that website that had the truth tables, I believe we have the truth table for distribution. Yeah, there it is. So remember that in this case, the triple bar means equivalent to that. So that's the same thing as the four dots. And so you can see that, in fact, these are equivalent because we get all T's, all trues under that triple bar, the equivalence bar. So no matter what the truth values are, these are going to be logical equivalents. And so there's the truth table to prove that to you. And so one trick here to remember this rule, and it is better to memorize all of them, is what is quoted, what is said exactly in the Hurley textbook. The operator that is at first outside the parentheses goes inside, and the operator that is at first inside the parentheses goes outside. So basically, what we're doing here is if we think in terms of parentheses, we just switch the operators, right? In this part here, the dot is outside the parentheses, and here it goes inside the parentheses. And then the same thing works with the other variation. Here we have the disjunction outside of those parentheses, right? And then here we have the disjunction inside both parentheses, and then we have the dot outside, and whereas here we had it inside. So that's a quick way to remember the whole thing for distribution, how basically the whole layout in terms of the variables P, Q, and R. Okay, and so the last one here is double negation, and this is probably the easiest one and the most intuitive one. So basically this says that P is equivalent to not P. That's tilde tilde P. And so if we take a very simple example, like for example, let's let M represent the proposition the milk is on the fridge. And well, we know that not M would be would represent the proposition the milk is not on the fridge, right? Remember the tilde is the negation. Okay, well, it's easy to see that if we say it is not the case that the milk is not in the fridge, we would have to have two tildes because we have the not here. Oops, let me go back. We have the not here, and then we have the not here, right? We have two nots, and that's why we need two tildes. And so that would have to be tilde tilde m, right? It is not the case that the milk is not in the fridge. Well, basically saying that it is not the case that the milk is not in the fridge is the same thing as saying that the milk is on the fridge, right? So those are logically equivalent. Logically, they're saying the same exact thing. Not m is equivalent to m, and vice versa. M is equivalent to not m. Okay, so this one is humorously one that a lot of people don't understand because sometimes they're with signs like this, for example, at my daughter's school, they're basically saying the opposite of what they want to say, right? You see the circle with that diagonal thing there already means no, right? So that already means no bully. But then we have another no over here. So here we actually have a double negation, which basically logically means that this is a bully zone, right? So there is a bully zone in my daughter's school. Okay, that's it for this video. Again, keep watching the videos, and I will follow this one up with a practice exercise video. So you will have the opportunity here to to practice these, and of course that's what your homework is going to be about. But I will have a video where I will show you how to apply these and practice them in exercise.